I can make it better. That is ultimately a hypothesis. They have to refine that hypothesis because it's not just I can make it better. We have to come up with what you are changing to make it better. There are tons of variables when making that pie. We addressed looking at ingredients. Are there other variables?
Yes.
Yeah, like what?
The combination of the ingredients by the temperature of adding them. There's what?
Temperature. What temperature are you mixing those ingredients at? Okay.
For how long?
How long were they cooked? Did you just throw it all in a blender and then throw it in a pan and put it in the oven? Okay. There's a lot of different variables that go into it. Some of those variables are obvious. In the case of a pie, we can see that and hold that. How many of you can hold a molecule? Those are being like, yeah, I can hold, a fistful of water. That's not one molecule. Okay? Chemistry is something that is inherently abstract. Okay? We are modeling what we can't touch and control at single atomic level, and we are trying to create hypotheses. This means there are thousands of variables, some of which are obvious and we know to control. How much water should I put in? Okay? Did I know to make sure that the water should only be oriented in one direction? Okay? Maybe not. Was that important? I don't know. How would I find out?
By testing it.
I would test it. So after the hypothesis, we get the experiment. Okay? So we now build that hypothesis. We run an experiment to test that hypothesis. Okay? Interestingly enough, as I've continued to do this lecture, either people have had spoilers by looking at the slides online, which is okay, or science is being taught differently. Okay? But if we think about what our textbook said, after the experiment, where does it go?
To peer review.
Okay, we could go to peer review. So ultimately what you've done at the end of that experiment is you have now created a theory that you could ship out for other people to then test. Okay? Or a natural law. Like those are the two big pockets that scientific method leads into. Okay? And when we think about that, that is a very linear process. I observed, I made a question, I made an experiment, now everybody proves that I'm right. Okay? That's neat. Okay? There's a problem with that theory, though. Okay? Particularly when it comes to you as budding scientists. You do the same thing. You observed, you made a hypothesis, you did an experiment, except what happened to your experiment? It failed miserably. What is your conclusion of that?
Edit the variables. Try again.
Okay? Some people are edit the variables. Do it again. Your hypothesis is wrong. Okay? How many people in here are bad chemists? So, what was your experiment? You've tested this before. Why are you bad chemists? Why do you think you are bad as a chemist? You didn't get the results that you wanted. You mean your experiment failed? Yeah. Okay. And you look at the literature, our textbooks, and they say you go observation, hypothesis, experiment, success. And what did you do? You failed, so you must suck as a chemist. Okay? That is a horrible model to push, particularly to people that are starting to become scientists, because that is not how it works. You fail. The most brilliant chemists fail. Right? And they have to go back and they adjust their hypothesis. So those people being like, well, you adjust the experiment, you change the variables, you attempt the hypothesis. Sounds like you've already started to move through some of that scientific thought. There was still a good half to 3/4 of the class that rose their hand and said they're a bad chemist. You're not a bad chemist. It's going to fail. Okay? What you haven't been told is that it is going to fail and that you now need to change your approach. You go back, you change your hypothesis, and you retest it. You're now a better chemist. What happens at the end of that experiment? It fails again. Okay? The most honest scientists out there, okay, and even then it's probably a bit of an understatement, have said that they have spent their lives failing 99% of the time. Okay? If you get a 1% in this class, that is a failing grade. Scientists are failures. Okay? But what they keep doing is they keep going back to it. They keep making those adjustments. They keep trying to learn from those mistakes that they made to improve. Why do they do that? That 1% of the time that it actually advanced into a scientific theory or a natural law was such an awesome feeling that they will go back to the drawing boards and fail a whole bunch more. Okay? You just haven't made your breakthrough yet. Okay? That's what I want you to find. Okay? You will go through and fail and struggle. But what you need to do is remember that you have to go back, make an adjustment, change, and advance. Okay? For some people, you're going to get an A in this class, you'll be like, I didn't fail. Cool. What happens when you move to the next chem class? The next one, or the next one, or the next one. Those people that have failed Chem 130 are probably in a better state to advance through science than someone getting an A in it. Because the someone getting an A is just going to keep moving through and never really hit that wall. Or when they hit that wall, what happens? They shatter and they're done. I was so successful in the past, now I'm not, I must be the failure. No, okay? You're not the failure. It's all about adjusting and changing that process going forward. Okay? Who knew you were getting a self-help class, right? Okay? I'm helping you fail. Exciting. So, what is chemistry's role in science? Okay, every science is going to say they're the bridge, but chemists are really the bridge. Okay? We get physicists and mathematicians playing with abstract crap that no one can understand. We get biology and other stuff, okay, dealing with the bigger things that we can grab a hold of and physically control and helps us understand. Okay, engineers I put with the biologists. Okay? And I'm sure engineers are like, that's crap, we're the bridge. Yeah. Go tell it to the other side of the rock. Okay? Chemistry is that bridging. It's taking that abstract stuff and tying it to reality. That's a hard connection to make because people in reality don't see the abstract. People in the abstract don't see reality. Okay? This is why Picasso cut off his ear. Take an art class. Right? We get weird things happening. Trying to bridge those two worlds is a challenge. And that's where I would argue chemistry sits. Okay? This is why chemists can get hired into virtually any job position. Okay? My wife is a materials engineer. What does that mean? She's a chemist that didn't want to have to sell her position. Okay? By adding the word engineer, people go, oh, you must know stuff. Dude, she's a freaking chemist that didn't learn enough chemistry, so they appended the word engineer to the end of it. She doesn't listen to my lectures. It's okay. Right? Chemists bridge that gap. And chemistry is a wide range at varying levels of bridging that gap. Because you get physical chemists that are way deep on the abstract side of it. Okay? And it's really cool, the stuff that they do. But they are way freaking abstract. Okay? You get people like the biochemists that are way on the biology side of it, that are looking at small applications of chemistry, but really how that physically manifests. Okay? Then you get organic chemistry, which is the pure middle, okay, that ties everything together. That's my background. Organic chemistry, of course, you got to be the pure middle, right? Everybody's the pure middle. Inorganic chemistry, okay, probably the step above organic, because instead of just looking at like 10 elements that we do in organic chemistry, they say, well, let's look at all the elements. Okay? That's materials. Okay, so we're looking at how those different fields all branch out and connect back to chemistry. Okay? So, what do you see? Someone was brave. It's a terrible picture. Oh, pun. Now I'm with you. I was like, there's no pun. It's just a picture. Oh, yep. Never mind. You would think I would remember that. I wrote the slide. Okay, someone said, I saw a sheep. Interesting. I didn't put those two things together, did I? Okay, the sheep is actually what it is. I would argue that's kind of qualitative. One is quantitative. Well, what's quantitative? Quantity, typically tied to a numerical value. Okay, so we could have talked age. That was I don't know anything about sheep. 13-year-old sheep. Okay. What else could I put in here? You're like, I don't want to be wrong. There's no wrong. Trees, I'll accept that. The focus was on the sheep, but trees are there. That's absolutely valid. What's that? Color. I see orange. I see red. There's no freaking red or orange in there, is there? Color's too vague. What do you see? Sheep is a color? Shape is a color.
No, I didn't say color.
Damn it. Man. What'd you say the first time?
Oh, wait, I said color, but then I said
Okay.
do the shade.
So what's the color?
It's like an off-white. It might be a little dirty.
Ooh, that's interesting. Off-white, dirty white. Anybody notice an issue with our qualitative potentially? Eggshell. Gray. Anybody colorblind? Qualitative could be a very difficult thing, particularly when it comes to color. Okay? What about the quantitative? What else could you throw in this? I'll accept that. 2. Closer observation. There's a second one hiding back there. What else? How about the weight of the sheep? Anybody know anything about sheep? Can help me out? What's the weight of that sheep?
You're probably looking at 170.
That is a lot different than I have ever specified for the weight of that sheep. So thank you for that. We'll try and remember that. 170 pounds, presumably? Pounds? Yeah. So 170 pounds. Okay, that's interesting. LB, is that pounds? How do you spell pound? POUNDSLB? Okay. We're using abbreviations, so we have to watch out for the language tied within this. Chemistry isn't just about molecules, it's also about the words that we use to describe what we're observing. Okay. What else could we throw in here? Anybody watch? What's that?
Like other than like, so
I'm
it's like
getting to that. What's the show with the minions? Despicable Me. It's a fluffy sheep. Why would I care about it being a fluffy sheep? Okay, we could mention that it's got the wool. Okay, so we've got some observations here. Which of those is more important?
Depends on what you need, or sheep both.
Okay, so we've got a couple people not taking the bait and saying it depends. Okay, so that was the front of the classroom. Sorry, I know, I got you. Let's get the back of the classroom. What do you guys think it depends on? What you're experimenting, the value, the hypothesis. If we tie this back to kind of a writing aspect, what is the context?
Depends on what you want to extract from
Okay.
what information you extract.
Who is making these observations? A butcher makes these observations. What's the most important thing? Probably the pounds, because they see that pounds and they go, how much about sheep do you know? Are you on the butcher side of it or the?
I'm major though.
Okay. You see 170 pounds and you see
Cutability, you're looking at 90 pounds of meat on the rack.
90 pounds of meat, okay, which you're probably then adding to that 90 pounds of meat that I can sell at X price. So you're seeing a dollar sign associated with that, okay, with the meat of the sheep. Did that right? Is that singular? Shope? So the weight is the most important thing. Well, what if you are a knitter? Because I don't have a better description than that. A tailor. The amount of wool, perhaps the quality of the wool. That sheep is jumping through a bunch of woods. I see some thorny things, man. That's going to get in there. I'm going to have to pick that stuff out of there. Right? I have to clean that up. So depending on the context of what our observation is and what we are trying to find, we could come to drastically different conclusions. So we have to be very careful when we frame science to understand where we are trying to go with it and to try and allow us to not bias that decision, okay, or those control or conclusions. That is a challenging thing to do. Kind of make sense? Cool. So, qualitative observations tend to be the easiest ones to make. They're also the ones that most people ignore when it comes to science. Qualitative observations are insanely valuable. 70 to 80% of life, what you've seen is what? Water. Right? You have the qualitative observation that water is all around us. It makes up 70 to 80% of our existence. Okay? So that observation in and of itself is an awesome starting place for chemistry. Okay? What makes water so special as our starting place for chemistry? What's that? It makes up our bodies. What else?
Soluble and other things can mix with it.
We could see some other stuff mix in it. Really? Salt mixes into ice well?
At normal conditions.
Okay. So, talking about some conditions changing, why might that be important? What have you got?
It's most dense as a liquid.
Okay. Bringing in some observations about it, getting in some density, which is now quantifying. We're still qualitative, but I like the conclusion of that. It's most dense as a liquid is actually where it's most dense. It's an interesting change. Okay. Liquid is qualitative. Ice was also a qualitative observation. What's the difference between liquid water and ice? Solid. The phases of matter. Why is water so interesting? How many different substances that you're aware of have you seen on a daily basis as solid, liquid, and gas? Okay. Water is one of the very few. Okay, so water tends to start our basis for all of those. Most forms of matter can oscillate between any one of these, but a lot of that comes with the standard conditions. Standard conditions is a questionable statement. It's really standard with wherever you are. Okay? And for the most part, wherever we are, we could probably hit at least two, if not all three, of those different states of matter. Okay? So what observations could we make to help us differentiate those states of matter? What happens to the shape of a solid?
It's rigid.
It's rigid. Okay? The shape doesn't change. It's frozen, there it is. What happens to the shape of the liquid? It changes. Changes depending on the container it's put in. How about the shape of the gas?
Fills any given space.
It fills any given space, meaning the shape is constantly variable. Okay? What about volume? Volume of the solid, if its shape never changes, okay, it's fixed. What about a liquid? Its shape changed.
Doesn't matter.
It doesn't matter. While the shape changes to occupy the shape of the container, it only occupies to the volume of that liquid. Okay? So our volume for a liquid is also constant. How about for a gas? It fills whatever container, so it's constantly variable. So we could start to make some kind of approximations if we were to draw things out. A solid, okay, we might put in a very rigid structure. For a liquid, is it going to be as rigid? No, it's going to depend on the container we're in. I know it's a goofy looking container. Okay? There's going to be a little bit more motion associated with it because it's filling that container. Kind of, sort of. What happens when we go to the gas? Okay? In that same container, that's close enough to the same container, it fills the whole thing. That starts to give us some information about density, which is a relationship between mass and volume. Okay? For an individual volume, the mass of a gas is going to be less. There's less particles there. Okay? What about compressibility? What does compressibility mean? Those people looking at me, that was kind of funny, right? Like squishy, compressed. Jeez, guys, killing me. What happens to the compressibility of a solid? It doesn't compress. Why not? To compress, what do we need to have? We would have to have that space. Do we have that in a solid? No, which means we get minimal compressibility. What happens with the liquid? Okay, we don't get a lot of compressibility with the liquid. Will we get more than a solid? Typically. Will we get anywhere near the same amount as a gas? No. Okay? So what we're trying to do is make these big, broad observations to come up with these bulk classifications and then try and whittle those classifications down. Okay? So, matter. We've got our solids, liquids, and gases. We can now start to divide these up across some characteristics. We can get matter as a mixture, which is a spatially linked system. Okay, do we understand spatially linked? No? We are all spatially linked. Mikkel? Yeah?
Yeah.
Okay, you don't have to say anything. I was just making sure.
Cool.
Mikkel and I are spatially linked. Okay, we are a mixture. How do we know we are spatially linked? Yeah, we're right next to each other. There we go. Cool. Spatial. It's where we're located roughly. Pure substance, chemically linked. Okay, we had half the class saying you were bad chemists. Okay, so you don't understand chemistry very well if you think you're a bad chemist. If you don't understand chemistry, what are the odds you know what chemically linked is? That's a crap definition to use, isn't it? Okay, Mikkel and I are not chemically linked. Sorry. Okay. How can we establish that chemical linkage? Okay, let's pick me. What is chemically linked to me?
Water.
Hair, DNA. You guys are going kind of small. Let's go big. Let's pretend my arm was spatially linked to me and not chemically linked. You're like, oh God, yeah, there we go. You're starting to see the analogy here. If my arm was spatially linked, what could happen? It could just fall off. That is the spatial connection. It is not chemically linked to me. Okay? If my arm just fell off, you would freak out because you know my arm is chemically linked to me. That's a chemical linkage. Okay? So what happens then when we kind of move through these things? Being able to identify them, coming up with analogies is one thing, but being able to see them in an actual molecule is a lot harder. Okay? I hate that we talk about this now, but it's one of our kind of origins, so we kind of have to go through some of this. So let's take a look at that mixture of spatially linked. Okay? We get two classifications. We could reference it as heterogeneous and homogeneous. Okay, I want to make a new mixture. Lucas. Raise your hand. This is Lucas, everybody. Say hi, Lucas.
Hi.
Okay, new mixture. Okay. What do you think? Heterogeneous, homogeneous?
Heterogeneous.
Like you might need a classification on that, right? Let's compare that to the other mixture we had with Mikkel in the corner. You want to raise your hand? Say hi.
Hello.
Hi. What do you think? Two mixtures. Mikkel and myself? Or Lucas and myself? We are pushing some boundaries on this, so I do apologize with that, but see what you can come up with as classifications. What do you think?
The sexes are the same.
Okay.
X one.
Male, male, female. Heterogeneous, homogeneous. Okay. Homogeneous, no visible separation. There's clearly a separation, just for the record. Okay. We are clearly different. Okay. But we could group that as a homogeneous relationship versus a heterogeneous relationship. Okay. How can we apply that to chemistry? I wonder if there were ways that we could classify chemical substances that we maybe just addressed on the last slide. Like, the last slide was like 20 minutes ago. You take so long. Solid, liquid, gas. Okay? A heterogeneous system is a visible separation between two phases. It doesn't have to be two solids. It could be a liquid and a solid. That's a heterogeneous mixture, because I've now mixed a liquid with a solid. Sand and water don't mix super well, but if I put them in the same container, they are now by definition a mixture. They're in the same container. They will separate away from each other because they are a heterogeneous mixture. What if I took water and salt? Homogeneous. Why? What does the salt do? It dissolves into the water. So the whole thing has no visible separation between the liquid water and the solid salt. Visible becomes a question. We already addressed an issue of colorblind. Does everybody have perfect 20/20 vision? We are basing our classification on our ability to see. Okay? Questionable areas. Okay? But that's what we're attempting to do. We're trying to come up with as best classification as we can work with. If we move over to pure substances, these are our chemically linked. Okay? Compounds are at least two elements. Okay, well, what is an element? Gold is an element. Is water? No. You're like, what's he doing? Right? We've got a periodic table. I may regret this. Okay? Those are all of our elements. Okay? It would be nice. It'd be nice if we could clearly see them. We're working on that. Okay? We're going to see if we can't move it over there. Okay? But those are our elements. So when we're looking at compounds, we're looking at two elements that are chemically linked to each other. How do we know they're chemically linked? What is the formula for water? Is hydrogen chemically linked to water or oxygen? Yes. What about that makes you think it is chemically linked? Are they chemically linked? I heard two answers, so cool. Are they chemically linked? How do you know they're chemically linked? Careful. How do we know they're chemically linked? They're right next to each other. That space makes a huge difference. You put a space in there that goes from water to hydrogen and oxygen. That's a really big deal. Okay? So small, subtle changes in literally how we write things will change how we interpret them. So we do have to be careful with how we're representing these things. So compounds are at least two elements that are chemically linked. How do we know they're chemically linked? We would see those symbols written very close to each other. Okay? Heard an awesome suggestion. They are bonded. Is that H2O?
Yes.
Is that H2O? So for half the class knowing nothing about chemistry and being bad at it, I'm kind of wondering why you knew that was all of a sudden different. So there's an interesting statement. There's not two H's. You're telling me on the board right now what I wrote in red, there's not two H's.
Like connected. You know what I meant.
Okay? Knowing what is meant versus what is drawn versus what is said is a challenging aspect, and that is one of the things that we have to dig with and deal with when we're looking at chemistry. So we have to be as precise as possible. You knew that that line meant a chemical linkage. Okay? That is a chemical bond. Do we know what a chemical bond is yet? No. But do we know what it looks like? Yes, it's a line. Okay? Are all lines chemical bonds? You don't know. Didn't I just draw 3 lines? Okay? So we have to consider how our knowledge is represented and put forth. And for those people thinking that you are bad, what's happening is you're getting lost in some of that language. How do you learn that language? Practice it. Okay? That's what we're trying to go through that class. And anytime you've gone through and failed, you didn't have enough practice to figure that pattern out. Okay? And you may not have had someone sitting there to be like, no, this is what that meant. Okay? So don't blame yourself. Blame the people sitting next to you. Okay? So, element, one type all by itself. Compounds, 2 elements. Okay? Anybody know what oxygen gas is? Formula. Element or a compound? And we get a bunch of different answers again.
It's a compound.
Compound is at least 2 elements. What are the 2 elements? Oxygen and oxygen. You're telling me oxygen is a different element than oxygen. No, what is it different? Oh, I think I might have heard it. It's a different
You said it didn't have.
atom.
It had to be different elements.
Is the language important? Yes. O2 is an interesting one. Okay? It could really kind of push in sort of 2 places. I would argue O2 is an element. It's not a compound. It's a molecule. And what the hell is a molecule? A molecule is a collection of a bunch of different elements. Isn't that the same thing as compound? No, because a compound is saying different elements.
Do they say they are different elements? Is there somewhere where that's...
I don't know. It's language. So this is one of those things on where that language becomes dicey, and we have to watch the language carefully. Okay? Don't blame chemists for you not understanding chemistry. Blame English majors. Okay? So, classifications for our elements. We get metals, metalloids, and nonmetals. I'm really not happy that we don't have a periodic table there. Okay? We compare those across. Are those the same? No, we get most solids or gas. Okay? Luster. What is luster? Shiny. What is dull? Not shiny. Yes.
Can a non-metal also be a liquid? Isn't there one?
We'll address that. Notice, there were 3 phases: solids, liquids, and gases. Anybody see liquid? No, so it must be wrong. What does most mean? Not all.
It was
Okay.
at least 51%.
So, unfortunately, there are some gray area in all of these categories. But these are bulk categorizations. Okay? There are gray areas between things. Okay? Those gray areas cause problems when we look at chemistry. It also causes problems for everybody else when we look at our everyday life, because we try to pocket people and say, you are white, you are black. Okay? That's not necessarily our identities. And we have to realize there's a lot of wiggle room that can happen within these. Okay? And what we have to do is push even deeper to understand those connections. These are our first superficial passes. This is 700 years ago. Have we learned more? Yeah. Okay? Will we learn more? Maybe. Okay? But we're coming up with the best categories we can to explain the majority of what we're evaluating. Okay? Conducts heat and electricity. What substances conduct heat and electricity? Anybody know an element? Copper and gold and silver. Okay, how do you know copper conducts heat?
That's what they use in air conditioners. Copper.
Fair enough. No really rich chefs, I guess. Really nice pots are made out of copper because they conduct heat very, very, very well. Okay? They could also make them out of silver and gold. That starts to run into some other issues. Okay? Electricity, effectively the same thing. Copper, gold, silver are all metals. Guess what this first column qualifies? Metals. The other column? Not metals, because for the most part they are direct opposites, right? Okay? So we could use the language of metal and non-metal to help us qualify those things. Okay? What do you think these look like? Examples at the top. I see some solids. Are they lustrous? Are they malleable? Can you look at a picture and decide malleability? No, that's an interesting challenge. So you would have to run an experiment. Anybody want to throw it out there and take a guess? Non-metals. Good call. Next one. There are three names up top. We started with those, went to those. Metaloids. What's the problem with the metalloid? They do in all categories. Okay? So they're a giant mix. So we could look at the properties and be like, the properties of this substance carry characteristics of both. It's probably a metalloid. Okay? The physical observation becomes too difficult to nail down. Okay? How do we see this on a periodic table? Periodic table's behind the wall, so conveniently we've got one here. Okay? We've got some important points to note out here. I think I hit that right. There is a staircase on your periodic table, okay, now drawn on. That red staircase is a pretty hard line. That hard line represents the difference between metals and non-metals. How do you know which one's which? Copper, gold, silver. You all acknowledged were? Metals. Where are they? On the left-hand side, which means the right-hand side must be non-metals. Where are the metalloids? On the staircase. In the transition point between metals and non-metals. Is it perfectly on the staircase? No. That's why I don't like labeling metalloids. Okay? And we could easily just look it up, okay, depending on the color pattern. So we've got these bulk classifications that we need to relatively quickly be able to look at. So that when I ask for magnesium, you can tell me it is? Okay, let's try a different one. Sodium. 11, that's a good hint. Sodium is?
21.
Metal. Why? Left-hand side. I picked sodium as kind of a weird one because I figured some people might actually know the symbol for that. It's a little of an odd one because sodium, spelled S-O-D-I-U-M, has the symbol Na. Very commonly tested on because the symbol doesn't match the name. Okay, it actually does match the name, natrium, in Russian, I think. Okay? The symbols don't necessarily match to the names, which means what do you need to be able to do? You need to be able to make that tie, because you'll be given a periodic table, you may not be given the names. So you have to be able to translate name to symbol. How many of you want to memorize? There's actually 118 of them. This periodic table is old. We got these guys. How many people were told that they were required to memorize all of the elements? Did you enjoy that?
No.
Yeah. I think that's pretty dumb.
I had to do it my sophomore year of high school.
Yeah, it's pretty dumb. Okay. You are required to memorize some. Which ones should you memorize? The first one. Hydrogen. Yeah, we should memorize hydrogen. Oxygen's a good one. Helium. Carbon. Potassium. I think I heard someone start to be like, this is stupid. Basically, sorry, close, but no cigar. The first 36 should be committed to memory. Are there more that you need after that? Yeah. Okay, silver, gold. There are some all over the place. Right? But you don't have to memorize 118. You're probably in a 50 range. Open up that file, Elements for Memory, and it lists all of the elements. Some of the elements are bolded. Why are they bolded? Those are important. I was given that list when I started here, and when they gave it to me, they said, this is what I expect students to have memorized in the periodic table. And I was like, cool, it's not all of them. Okay? And then I said, too, okay, I don't think everybody should have to memorize those, because there's a bunch that are just useless. So I went through and bolded some. The bolded ones, if you just want to pass, and this is all you need, that's probably good enough. Okay? You want an A or you need more chemistry, do the sheet that I gave you. Don't do 118. Okay? Start working on that, because you need to be able to name them. Questions? You don't have to memorize any numbers with them, at least not yet. Okay? And by not yet, if the number's up there, don't memorize it. Okay? Kind of, sort of? What else should you tie to that? Non-metals versus metals versus metalloids. Okay, what else should we tie to that we talked about at the beginning of class? Solids, liquids, gases. Where does it say solid, liquid, and gas on that periodic table? For those of you looking for the words solid, liquid, and gas, it is not present. But what I am frantically trying to do, is color code some stuff. When we look at the periodic table that is actually underneath the PowerPoint, you will see, I believe, this color coding. What does it mean? Noble gases are part of this. We actually don't need to know that content yet. We will by the end of Unit 1. The blue ones are liquids. The red ones are gases. The black ones are solids. The phase information is encoded on the periodic table. You have to know how to pull that information out. You don't have to have that memorized, because it will be provided to you.
That's at standard atmospheric pressure.
Standard atmospheric pressure and temperature, all that fun stuff. Those of you wondering what that is, don't worry about it. Yeah, that one's also kind of crappy. Okay, so